Very good. Elizabeth, the scene is for you. Yep, excellent.
Can you hear me?
Yes, we can.
Okay, great. Hello, everybody. Yeah, today's my turn to come up with an update. Hope everybody had a nice vacation. Just as a reminder, my topic is flow to friction and back in carbonate rocks, and I'm gonna specify on on carbonates, on dolostone and on limestone, and I want to investigate the frictional properties at condition remaining at the transition zone, but also on the deformation mechanism to study the deformation mechanism active at unstable slip behavior. At the right side of the screen, I also put a sketch of my rotary shear, the rotary shear apparatus that I use, and where the gouge is located, just so everybody knows what I'm talking about. This is an experiment my supervisor did, but I'm going to discuss the data because I did some microstructural analysis on the experimental products. He did that on Solnhofen limestone at different temperatures. He also did some normal stress steps at velocities between 16 nanoseconds per millimeter and 144 nanometers per millimeter. I wanted to more talk about the experiment I did, which was on dolomite gouge. I was focusing the last time on calculating the friction coefficient, which you can see in the plot I show here. And I wanted to show you a few things that stood out to me, which I found interesting. So here I plotted all the temperature steps where I did the same velocity steps, and somehow it looked like the one at 450 degrees look a little bit similar, but the friction coefficient at 600 degrees looks quite different from the 400 and 500 degree steps. The mean frictional coefficients seem more stable, and also interesting are those oscillations that you can see, which are not typical for friction experiments. So I'm gonna zoom in a few other sections, and yeah, exactly, you can see the oscillations throughout the data. And it somehow seems like there's a frequency dependence on velocity. And I picked this part because it does not show that the amplitude of the oscillation is not that high. So you can somehow guess the mechanism, and it somehow looks like it is velocity strengthening, but I didn't do the rate and state friction model yet, so it could be just like after I do some correction, it won't show this behavior.
Can I stop you? Sorry.
Yeah, sure.
So you mentioned it's velocity strengthening, but I mean you're showing something else because from just before, as you increase the velocity with the displacement,
Yeah,
you
exactly.
see that the friction is dropping, so it's velocity weakening on the left.
Here, I'm talking about the right part here.
Okay, yes.
Yeah, the instantaneous reaction is, you're right, velocity weakening, but it goes further up, and I was wondering if it has reached steady state or not. So I thought, is it now velocity strengthening because like at a further stage with more displacement, it has a higher friction coefficient than before.
Okay, but then if it's velocity strengthening, you wouldn't see any stick slip at all.
Yeah, this is also I mean, this is the most interesting finding, but I found a paper by Weeks from 1958, and he's observed the same behavior in dolomite. He said he also observed those oscillation, which are kind of unstable behavior, but also velocity strengthening behavior after rate and state friction, the model. So yeah, this is a big question that I don't know the answer to.
Okay.
Yeah, but we also see like some other behavior, and I zoomed in this part because you can clearly see the amplitude and frequency, and at the left side, the amplitude and frequency dependence on velocity. That is, with higher velocity, the frequency tends to be higher and the amplitude lower. And on the right side, you see I mean, it seemed to be velocity weakening at this part. And I also brought some microstructures that I did. First, these are some EBSDs of the experiments of my supervisor, which I talked about at the beginning. And I did the IPF, which is the inverse pole figures, to see any directional dependence. And it doesn't seem that it has any. This is the thin section sheared at 600 degrees. And here for comparison, the one at 500 degrees. And I also plotted the one in Z direction, just so you know how it would look like if the sample would show, or the minerals would show a change in orientation. And those are some SEM images that I did on the dolomite of the experiment I did, which I talked about a second ago. And here you can clearly see a boundary shear at the top of the thin section. And since the shades indicate chemical composition, I was wondering about that. So I also did some energy dispersive X-ray spectrograms. So the main finding here is, and it just does not fit in one slide, that the magnesium and calcium content seem to vary in the different shades. Like I don't know if you can all see that, but the yellow dot is the position, and then those are the chemical, right to it are the chemical compositions. So my question was, is there some chemical processes going on? But to verify that, I wanted to do some the same measurement in unsheared dolomite or deform it at lower temperatures to compare it with it. yeah, those are some next steps that I'm going to do, which are experiments on the Solnhofer limestone, but on gouge. So I can compare it with the rings. Also lower velocity experiments, and lower temperature experiments, and more analyzing of the SEM and EBSD figures that I showed. And for sure the rate and state friction analysis. Yeah, that's it from my side.
Okay. Well, when you mention rate and state analysis, what do you mean? Changes in velocity? So, is that right? Or
Yeah.
how the evolves with steps in velocity?
No, I mean the rate and state friction model, which I didn't
Okay.
do. I just have the data, and then there are some corrections that you have to do to obtain the A and B values.
Okay, which is okay, but it's fitted on changes, I mean step changes in velocity normally. Is that right?
Yeah, I have to have the changes, but I have the data of that, so I have just
All
have
right. Okay. Yeah.
to do the modeling.
All right. Okay. Thank you. Are there any questions for Elizabeth? So actually, yeah. Go. I don't know who's talking.
Michele, so nice. Hello to everyone. I have just a curiosity about the last part because at 600 degrees C, I would expect the dolomite to the carbonate to start the. You have this kind of two steps, no? The carbonation reaction and to produce magnesium calcite and then periclase. So you did you see anything like that in the SCM? Like something brighter that could be magnesium calcite or periclase?
Yeah, this is, oh, sorry, I didn't mean to do that. Yeah, okay. Yeah, I mean, the SEM showed like lighter parts and darker parts.
Yeah.
And I interpreted that as the like the chemical reaction.
Okay,
Because
the carbonation. Okay.
exactly, yeah. And yeah, the right side also says tells you the elements, and if I go back and forth, you see the
Yeah.
magnesium and calcium content seem to.
So these are the dolomite grains that are getting replaced by magnesium calcite and periclase, probably. Yeah.
Yeah,
Okay.
I don't know exactly, but I will look further into
It
that.
will be interesting to see. Yeah. And then the other question was about the strain in your experiment. If you think that because you are having an experiment sleeping now and you're seeing a different mechanical behavior, but sometimes maybe you can have could be nice to have to stop your experiment at different steps
Yeah,
to see really what's the mechanical behavior, taking out the effect of the strain. I mean,
yeah,
but
yeah,
that's something you will do for sure.
yeah.
Thank you. Thanks a lot.
Thank you.
Okay, good. Any other question for Elizabeth? Okay, so maybe can go ahead and have Nolwenn showing us what she's up to. Nolwenn, that's your turn. You're still muted. Yep.
Yeah. Okay. Can you see my screen?
Yes.
Okay. Hi, everyone. So just a reminder, I'm working on the fault damage zones in carbonates and the link to the seismic cycle. So first, Happy New Year. And second, so I was working in Padova, and now I'm not in Padova anymore. I moved to Munich. So now I'm working with Rachel on Seisol in Munich. Okay, so what I've done the last months is a full dataset, like a catalog. Yeah, I can. Yeah. Oh, sorry. Just moving? Yeah, okay, good. So I'm working on the Central Apennines. You can see on the left the main active faults, and on the right the faults I'm working on. So there's 8 different faults. Vado di Corno is one with the most data we have. The lens fault is about 20 kilometers, and the damage zone length is between like some meters to 400 meters. We can observe step overs, and also Vado di Corno is a normal fault cutting a thrust. The displacement is about 2 kilometers. And so just to show you, I will speak more about the damage zone later. So you can see here the fault core, here the damage zone, here it's Gran Sasso. So we can observe 3 or 4 segments in Campo Imperatore. So can you see my mouth?
Yes.
Yeah, okay, good. So here is the fault. And so this cut is this one. This one is here. And we can observe that there is a displacement along the fault. The displacement is bigger on the western part. As I told you before, we observed step overs, and that's what I want to model, this kind of geometries with SISO. That's why I'm here in Munich, and also try to model like simple geometries like this, like a normal fault cutting, cross-cutting a truss fault. Okay, so for the Venere fault, more in the south, the fault length is about 10 kilometers. So they are all small faults. And there is also oversteps and a displacement of 600 meters. There is also fault segments. And we are in the calcare massiccio, so limestones from the Jurassic. So another one, the Rocca-Pretoro fault, we can observe like 3 fault segments, and the length of the fault is 10 kilometers. So for this one, we don't have a lot of information. Just like 2 papers are speaking about it. And we have a displacement of 270 meters. For the Subicuana fault, fault length is the same. The the length, zone length is about 230 meters. And we can observe like on echelon segments plus step over. And okay, for the Campo Felice, so same information, the fault length of 6 kilometers, mean damage zone length of 400 meters, and a displacement of 1.5 kilometers. So another one, oh, sorry, yeah, here, the Monte Marine fault, so in the north, we have like a full length of 14 kilometers and a displacement of 1.5 kilometers. And also the displacement is different along the faults. Yeah, so just to finish a bit. So in the middle, we have sorry to explain to you. So we have the slip zone. So it's a really thin zone where we can observe stria. And here we have like a matrix, whitish with clast. So after that, here, the green part, we have the fault core, which accommodate most of the displacement. So we have cohesive rocks. For the thickness is about like some meters. And color is we have a white matrix, so limestone with gray clast from the Ostwar rock. Sorry. Yeah, so the clasts are thinner near the fault and bigger farther, and it's impossible to recognize the Ost rock, and the rock is really damaged. So here we have the damage zone with like a gray color. We can observe joint veins, and for the thickness, as I told you, it's between like it's around 0 meter to several hundred meters. We can recognize the bedrock, but with damage, you can see we can follow a bit. There is also like nodules here, with a lot of fractures, but we can still recognize it. And of course, there is more fractures near the fault core, as you can see here on the picture. And for the bedrock, or the host rock, it can be a bit damaged, but not that much, as you can see here. Okay, thank you.
Just a question. So you quote several papers that
Yes, yeah.
that give estimates for the fault zone length. I guess, I mean, so it's all on the field. So I guess everybody has his own criterion to decide where to stop the damage zone. So is that, do everybody use the same type of criteria, or is it like, you know, quite subjective?
I only took information from people that are using the same criteria. So, yeah. And also because Michele worked on Campo Imperatore, and so it was his technique. So
Okay, and the other papers follow the same. So okay, the same method then, I guess.
yeah.
Okay. Well, I was surprised that, I mean, there doesn't seem to be such a strong link between the length of the damage zone and the size of the fault itself. At some stage, you have a segment of 6 kilometers, and the damage zone is is quite wide. So just wondering if I guess you should expect some relationship between the length of the segment and the length of the damage zone, don't you?
Yeah, but I think it's hard to, because I have like 6 folds, so I think it's hard to do a correlation with 6 folds. But I mean, I will see when I will start numerical modeling, it will be easier to do things and try to understand if there is a correlation or not.
So what are your next steps from there on?
Now I'm learning how to use Seesaw. And first I will do like basic geometries fold with the software, I mean with the code. And yeah, like the next month, I mean, yeah.
So you will stay in Munich for how long?
For 3 months.
All right, okay, good.
Yeah.
Okay, any other questions for Nolwenn?
No, just a curiosity, but are you planning also to do some field work, or you'll be use only the literature data?
I went on the field already in October, November, don't remember. But just for observations. So I think I will go again in June or May. Yeah, for observations, because but I want to, but I think I don't have time to do like field work and numerical modeling.
No, okay.
Any questions left for Nolwenn? Okay, if not, then Erwan, I see that you're somewhere there.
Yes. Can you hear me?
Yes, we can.
Okay, good.
Good. So I guess you can start with your lecture now.
Okay.
Enjoy.
Thanks. So hello, everybody. Okay, so first I have to share the screen, right? It should work. Okay, can you see the screen
Yes.
and my mouse?
Yes, we can.
Okay. Okay, for this, open then.
Okay. For everybody, I mean, don't hesitate, I mean, to have the lecture more lively, I mean, to interrupt Erwan. And again, you come from very different backgrounds, and I'm sure Erwan will possibly use, you know, terminology that you're not familiar with for some of you. So, I mean, just don't hesitate to ask for clarification. And it's important that, you know, the lecture, you know, is helpful for everybody. So, again, just take, you know, unmute your microphone and ask a question during the lecture.
Yes, of course. I try to do something with not so much requirements, but maybe it will be too low level. But okay. Anyway, we'll see.
I mean, that's a goal.
It's a difficult compromise to do.
Excellent. Okay.
Okay, so let's start. So today we'll talk about active fault and remote sensing. And so first of all, I will define what I mean by this active fault and remote sensing. So I'm Erwan Pathier. I'm from University Grenoble-Alpes in France at the ISTER Institute, and I'm co-advising Maike, who should be around. I've seen her. And yes, and I'm mainly working on active tectonics using remote sensing methods to learn more about this active fault and especially the seismic cycle. Okay, so first, by active fault, this terminology is somehow difficult to define. Let's say we can say that active fault are those that are producing earthquakes. So first consequence, that is active fault has potential for future earthquakes. But this potential is not clearly defined. The recurrence time of large earthquakes can be very large. It could be from hundreds to thousands of years. So future is not a well-defined word. And active faults also for the main one implies the existence of past earthquakes. But there is also no clear consensus about what time period we should consider to define what is an active fault, what activities it should have in the past. But let's say the order of magnitude is about up to 10 to 1,000 of years to hundreds of thousands of years. So, and in this case, we rely on the landscape analysis and paleoseismological record to study this because we cannot measure directly this past earthquake. The two illustrations here about the Magnolia active fault in central Italy. This is a view of the full scarp of this fault. It is a geological scarp. And if you zoom at the base of this scarp, you see most recent activities that are underlined by this more clear scarplets that correspond to about 12 meters here, that correspond to the activity of the last earthquake. And so if you have active fault, it means that we have also accumulation of stress and elastic deformation that accumulates that would be released during earthquakes. And this can be measured by geodesy. If we, in this kind of method, we can detect if you have a long observation period up to a level below the millimetric level. And of course, seismology can also help. So this is the active fault target we have. And remote sensing what I mean by remote sensing here, remote sensing is kind of a very loose definition that would be the acquisition of information about an object or phenomenon without making physical contact with the object. But if you take only this definition of seismology, there's a remote sensing, and a lot of method can enter. But here we introduce the following restriction that for this lecture, we will use Earth observation imagery using electromagnetic radiation, and we will restrict to airborne or satellite observation, because most of the technique that can use from airborne and satellite can also be used in situ. But in this case, we lose some advantage of the remote sensing from airborne or satellite observation. So here we will not talk about GNSS, GPS, or acoustic bathymetry, or gravity field, or magnetic field that can sometimes be included in the remote sensing. So it's just these two illustrations. One is a drone carrying some camera here that can be used to get information on the ground and retrieve some digital elevation model, the topography. And this is an illustration of two satellites flying information. This is our satellite imaging some strip of the Earth. Okay. So why using remote sensing for studying active faults? So it's what we will try to illustrate in the following slide. But this, broadly speaking, we can help, if that can help to answer scientific questions relative to active fault, and by complementing other ground-based approach. And the interest of remote sensing, as we have defined it, is that you can have both a global view ability, so all Google Earth, which is a composite mosaic of various sources of remote sensing imagery. But just to show you that you can have a kind of continuous view at the global scale, thanks to remote sensing. And at the same time, you can also have the ability to get a lot of details. Here is an example of DEM, a LiDAR DEM, with the scale is about here 300 meters, with a kind of a few tens of centimeter resolution. So this capability to have the global coverage and the very good spatial and continuous view, it's one of the major points of the use of remote sensing. And another thing is you have a different point of view with respect to ground observation, where you are in the field. You don't see the thing with the same perspective. So I think this field from the sky is very complementary. And with the remote sensing, of course, you have less accessibility problem, no political boundary problem. You can cover the whole Earth, and it's relatively low cost compared to some field work that can be done remotely. Nowadays, you have the capability to have access to imagery for free. It doesn't mean that the cost of this acquisition is null, but for the end user, let's say it's relatively could be relatively low cost. Okay, so the outline of the lecture will be the following. I will just first describe briefly the different kind of remote sensing data that are usually used for active fault studies. So we see optical imagery, radar imagery, digital elevation model, and the specific case of the LiDAR. Then we will focus on the use of remote sensing for studying the past activity of active faults that are occurring before the beginning of the acquisition of images. So in this case, this is one of the main use of remote sensing. We will try to read the landscape, to find the fault trace, and try to find some markers of deformation. And the last part will be using remote sensing for studying the present day activities of active fault that are occurring in between acquisition of the data. And we'll see two main approach. One is kind of a before-after comparison of data, and also a few examples of what you can do when you have more images here you just need one image after and before an event, and here time series analysis will be for more long-term analysis. And we'll finish by some example of challenge of using geodetic measurements from the satellite or airborne data in seismic hazard assessment. Okay, so let's start by the remote sensing data. So we can classify the remote sensing sensor in two main families for the sensor based on the electromagnetic radiation measurement. So first family is called the passive measurements. So basically, you will measure what your satellite is only measuring what is coming, the radiation coming from the Earth. And for optical imagery, it's mainly the sun radiation reflected towards the satellite by the surface of the Earth. So this will carry information about the properties of the ground, but also the topography, because we have shadow effect. So it will be useful to read the landscape. And the other family is the active measurements that are both emitting and receiving signals. So the instrument is emitting its own electromagnetic radiation toward the ground. And the ground is, you have a backscattering toward the satellite, and you will get also some images. So two kind of, the main sensor will be the radar imagery that also carry information about the properties of the surface and the topography, but also it has an additional information with respect to optical imagery. It has an indirect information about the sensor to ground distance. And the last one is the LiDAR, that is also an active instrument that carries also information about the sensor to ground distance. Okay, so let's just to give you an idea about what an Earth observation satellite does look like. This is an example of one of the biggest one for civil use that has been launched. It's called Envisat. So you see the size with respect to the people here. So it was before, of course, it's not completely deployed. You don't have the solar panel, but it was carrying a lot of instruments. Nowadays, the trend is quite different. So this is a picture of the satellite taken from another satellite, this time in flight. So you have, in addition to what we see in this figure, the radar antenna, which was not deployed here, and also the solar panel. So now the trend is more to have a smaller satellite, but more satellites. An example of this is the Planet Lab constellation that use hundreds of satellites. So this time we are this size, so a few decimeters, and these are produced at the kind of industrial scale. They produce a lot of them, deploy them in space, and so that you can have hundred of them. And the interest of that is that even if your satellite is on orbit, on this orbit, as you have a lot of them, is like you have always one of these satellites on any place here along this orbit. Okay. So far, I just say we use the electromagnetic radiation, but we have to go a bit into the details of what kind of electromagnetic radiation we are using. And this kind we will, with this terminology, we will distinguish two main domains called the optical domain and the radar domain. So basically the optical domain, so here on this axis, you have the electromagnetic radiation wavelengths. So here toward the micrometer, we are in the visible domain. So it's the portion of the electromagnetic spectrum we are sensible with our eyes. But you know that there is other part of the electromagnetic spectrum, like the ultraviolet or the near infrared, thermal infrared, and so on. And if you go toward longer wavelengths, millimeter to metric wavelengths, we are in the microwave domains. So when we talk about optical domain, it's cover all this portion of the electromagnetic spectrum. And when we talk about the radar domain, we are more on this portion of the electromagnetic spectrum. So this is the main difference. And on this axis, you see the atmospheric transmission that allow radiation from the sun to go up to the Earth. So if you are 0, there is no sun radiation arriving at the sea level. And if you have 100%, is almost everything is arriving on the sea level. So you see in the visible domain, we have of course capability. The atmosphere is letting the sun entering the atmosphere, but you have some portion of the electromagnetic spectrum where it's not the case, and that's why when satellites are designed, they measure only in particular bands that are the one where the atmosphere is allowing the transmission. And you see there is a big gap here between 100 micrometer and 1 millimeter, which is not used for remote sensing because atmosphere is absorbing everything. So you cannot not use it. That's why you have this big gap, and that distinguishes two domains. Okay, so when we talk about remote sensing imagery, there are several characteristics that are to be taken into account. I will not enter into the detail, but basically there is 4 main dimensions: the spatial dimension, radiometric dimension, the spectral one, and the temporal one. So I will just illustrate here the most maybe intuitive for you: the spatial resolution, the spatial dimension. With the spatial resolution, that means the details you can see in your image that corresponds, if you want, to the size of your pixels. And another point in the spatial dimension is the coverage. So even if your image is covering only 60 kilometers by 60 kilometers, you have still the possibility to combine different images to form a mosaic of image and to have a larger spatial coverage. In addition to this dimension, it's also possible for some instruments like the radar to measure some extra information, not only the radiometric information like here, but also what is called a phase measurement. And this measurement, I will go back to this later, but it contains information, indirect information about the distance from the sensor and the ground. And another thing that can be used is the polarization of the light. I will not talk about that, but know that you may have also another dimension which is related to the polarization. Okay, so let's start by the most intuitive one, the optical imagery, because it corresponds to what you are used to when you look aerial photos or when you take some picture. This is an example from the Landsat 7 images. You can see some streets, the cities here, and we are in the California near the San Andreas Fault. And here you can see immediately the interest of this kind of images for active fault. Here is highlighted by the arrows, the trace of the San Andreas Fault, which is very clear here in this case, which corresponds here to this very straight line with some particular feature along this line. So in terms of spatial resolution, we can go typically from tens of meters for this kind of images up to centimeter when you use airborne imagery, like with drone or aerial photos. From satellites, we are now up to several decimeters of resolution, typically up to 50 to 60 centimeters for civil application. So here you have some colors. So it means you have measured the ground property in different bands of the electromagnetic spectrum. I will not enter into the detail, but you can measure in up to hundreds of different bands that give complementary information about the properties of the ground. And you can see on this image, we are also sensitive to the topography. You can here see some topography because of the shadow due to the sun light that will help us to interpret this kind of images. In terms of temporal coverage, optical imagery, the usable time range for active fault is about 100 years. That corresponds to the beginning of the aerial photos. But I would say it's a kind of the best case, and it's rarely we can really use that long temporal coverage. So the first satellite image that are exploitable for active fault are the one from the Corona American imaging spy satellites from the 70s, and the first civil satellite are coming from the 70s with the Landsat program that is still continuing now, that ensuring a kind of spatial continuity. one of the difficulty in the optical imagery when you want to look at event like an earthquake and to look before and after an earthquake is the cloud cover that influence the effective revisit time. If you have a typical satellite with a 7 days return time, because of the cloud cover, if you have only one satellite, this map shows you the probability to have a cloud-free images. So in red, you have a high probability, but you see that in temperate region like Europe or Amazonia, you have a lower probability to get a cloud-free image. But if you take several satellites of the same type, you can go to better probability. So the effective revisit time depends, of course, on the number of satellites you are using. Okay, now let's move to radar imagery. So radar imagery is an active instrument. Radar means radio detection and ranging, and it has three main functions. So the radar will transmit a microwave pulse toward the ground and is able to capture the signal which is backscattered from the ground. And it will record two things: the intensity of this of the backscattering signal, but also the phase of this signal. And this is relative to the travel time, two-way travel time of this delay. In more details, the phase measurement, so when we are measuring this amplitude and phase, we can represent it as a complex number, so it's not important, but what you have to understand is there's two components in the phase. One which is due at the relative location of the target in the pixel which is illuminated, and another component which is related to the distance from the satellite to the ground. And the combination of these two, we will measure a combination of these two components. We'll go back to that later. One of the good advantage of the radar instrument is its night and day capability, and you can go, or you can image also through the clouds. So this is one of the big advantage with respect to the optical imagery. So for the temporal coverage, for civil observation, goes back to the 1992. This is an example of a satellite imagery about the volcano, the Fujiyama volcanoes in Japan. So here it illustrates one of the specificity of the radar images. Because we are looking on the side, we are not looking at the vertical, there is some geometric distortion in these images. They are more complicated to interpret than the optical imagery. But one of the things we will use is as it records the phase information, we will be able to measure some deformation using this kind of images. So the change from the distance from ground to satellite. Okay, so third type of data is digital elevation model. And indeed, digital elevation model are representation of the topography, and most of the digital elevation model are generated by a remote sensing method. I will go briefly through them. Just a vocabulary point, when we say digital elevation model, we talk about the bare ground, but in addition, if you have building or vegetation, we are measuring the top of the building or the vegetation. And if you want to talk about digital terrain model, which is only representing the bare ground, we make the distinction between the two because most of these methods are not only able to make DM, and we'll see that the LiDAR method is one of the only one that can get a good DTM. We'll see how. So to generate DEM, there is several methods. When using imagery, you use the fact that you can have different view from your satellite with respect to the ground, from different point of view. And this allows to generate some DEM. It's the case in optical and also in radar imagery. We will use this difference of point of view to reconstruct the topography. Another way to reconstruct DEM is to use a LiDAR method, which LiDAR means light detection and ranging. So we are, if you remember, in the optical domain, so mainly visible or near infrared. And the LiDAR is emitting some pulse toward the ground, and you are able to measure the distance from the sensor to the ground and to get a cloud of points that are allow you to generate very high precision DM, like this one. But a good point of this method is when you have trees, if you look at some point cloud, it looks like that. And you see that some of the laser signal are stopped by the trees, and some of them reach the ground. And if you analyze this point cloud and you look mainly to the last return, you are able somehow to filter the vegetation, which is not possible to do with optical or radar imagery. And so this is a big advantage of this method. You are able to get the bare ground. So this is a comparison between here and aerial photos, DEM, including the vegetation, and after filtering of the vegetation by keeping only the point on the ground, you get this information, which is very useful. Here you can see some tectonic feature, fault trace that were almost impossible to see in these two other images. Okay. Of course, depending on the method you are using, we have some compromise between the spatial resolution and the vertical accuracy. I will not enter the details. But you can refer to this slides, and of course you will have, when you have a better vertical accuracy, usually you have a lower spatial resolution. I mean, a smaller pixel size, and this is achieved by LiDAR methods or by drone photogrammetry, and at the other end you have large coverage and global coverage for satellite-based method. Okay, so now let's see how we can use this remote sensing data for studying past activity and active faults. So when I talk about past activity, I mean all the cumulative tectonic deformation that occur before your remote sensing data acquisition. So we have seen it's typically older than several tens of years. And in this case, remote sensing data will be useful to identifying active faults, because there is no exhaustive worldwide database of active fault, and also to characterize this active fault. And we can try to estimate some maximum slip, some fault length, segmentation, fault geometry, etc. So let's see some example. But before, the main idea behind that is that large landscape rupture can reach the surface of the Earth and leave a visible, measurable trace in the surface. And the cumulative earthquakes will somehow model the landscape. And of course, it will be in competition with erosion and sedimentation process that tend to smooth the surface. But if you have enough active fault, you will be able to see the imprint of the earthquake into the landscape. So just to show you an example of a surface rupture of an inverse fault in El Astam in Algeria. And you see here the effect of the erosion 7 years later, but still you can preserve this trace for quite a long time and be able to see it in your images. Just to see you another example on the normal fault in Djibouti, where you have the full landscape, the full scarp here, and you can have some here the last event. And this is correspond to the cumulative displacement we will be able to measure. And if you have enough precision in your images, you will be able to also measure some more recent signature of the fault activities. Okay, so basically, we will approach, we try to see to map the fault trace and to find some markers of deformation. So marker of deformation are markers where from which you know the geometry before the fault activity, and that has been offset or folded by your fault deformation. So here's two examples of fault trace mapping from either optical imagery for strike slip faults that usually have a specific signature with a very sharp, linear, and narrow surface trace. So you can see here the trace of the fault that can be mapped here on the left lateral fault zone. This is another example from Iran, using this time a shaded DM. You can clearly see here this trace with some local perturbation, but quite clear, which is not so easy to see actually so if you are here in the field, but when you have the global view, it's easy to map. What's happened? Okay, sorry. So marker of deformation could be, we will prefer some new morphological markers. It could be, or geological marker, or it could be also man-made marker, if you have them available. So you have two kind of families. A linear marker could be a river, a crest, or a planar marker like fluvial or marine terraces or alluvial fan. So here is an example of the principle of the analysis for here fluvial terraces. So let's say you have a river with some terraces here, fluvial terraces. If you have a fault that offset this river, and your river is incising, you create a new set of terraces. So at that stage, you have no deformation of T1, but T2 is deformed. And if you continue to incise, you will have, according to the edge of the terraces, a more or less pronounced offset of these terraces. And if you are able to date these terraces when they have been abandoned, you will be able to retrieve the slip deformation. So, of course, remote sensing alone here is a bit stuck if you don't have datation and so on. So this is one of the main limitations of remote sensing for this kind of application. You need to be able to date or to do some trenching or geophysics investigation to get more information about that. So an illustration of this, that is the case of the Coco Chile earthquake here. With image acquired after the earthquake. So in background, you have a 10-meter resolution spot. You can barely see some things because it's not, resolution is not good enough. But if you have a higher resolution, like these Iconos images at about 1 meter resolution, you can clearly see here the co-seismic rupture. And we will zoom on this area here when we will see some marker of deformation using alluvial terraces. So let's go on this place. So this is a zoom here. So here is, just for reference, a river. And here you can see that the fault trace is offsetting here some terraces. So this is the same area. So in blue, you have also the river looking from here toward this area. And you can see here the offset of the terraces that are bigger on the upper terraces than on the lower terraces, because here you have a cumulative of several earthquakes, and not just the last one. So you can analyze and estimate some slip rate if you have some datation of this. Another example from China. So this is the Landsat image. You can see here the fault trace is somewhere there. If we zoom in this area using sorry, yeah. If you zoom this area, the fault trace is there. You can see that the river here are somehow disturbed by the fault presence here. And if you, from these images, you can do some mapping and estimate the offset. And if you have access to the edge of the Holocene deposit here that are mapped in gray, you will be able to retrieve a slip rate. Okay, so last example with alluvial fan here. This is on the San Andreas fault. So this is a strike slip fault here that is offsetting a fan. So if we zoom on this area, you can do some more detailed mapping using this kind of imagery. And you can see here, for instance, that this alluvial fan was previously, this part was previously there, and you can measure some offset. And if you are able to date, again, to estimate some slip rate. Okay. Another example using from a reverse fault. So in this case, sometimes more difficult because the fault trace is more irregular and will follow the topography. So this is an example here of the fault trace with on the top a fold. Here is an example of the fault, and so this is an anticline here above the fault here, and this is the anticline axis, and this highlights where the fault trace reaches surface. But sometimes, for some, especially with reverse fault, you can have some blind fault that do not reach the surface, and that just creates some folding So in this case, you cannot necessarily map well where the fault reaches the surface, but still you can perform some analysis if you have some markers like river terraces of the folding of this marker. So for instance, here you are at T0, you have the first level of terraces. You have some activity on the fault, so the first terraces will be folded. So this is like that. And a new terrace is formed, which is not fold. And then at T2, you have again the older terraces with the most folded and the younger one which are not, the blue one, and the yellow one is less one. So if you are able to analyze these alluvial terraces and to measure their deformation, you will have some information about the slip rate at depth on this kind of fault. Just to illustrate that, this is an example in Asia. Here you can see in this figure an anticline here axis with some river crossing the anticline, so it corresponds to this case. And we will zoom on this area where some profile can be done on DM. And in this case, you get this kind of information. You see that the red one corresponds to the oldest terraces, which is folded more than the present day terraces, and using some datation of this information, you can get some information about the slip rate. Okay, so now let's move to the third part of this lecture, which is using remote sensing when you have deformation that occurs during your time period of remote sensing acquisition. So in this case, we will be able to monitor, go into the monitoring of the seismic cycle and not just the cumulative deformation of past earthquake. And we'll be able to isolate some phase of the seismic cycle that could be constituted of co-seismic displacement here. So here it's a graph that's schematic graph. So here it corresponds to the cumulative displacement with respect to the distance along a fault at the surface. So you can have past co-seismic event, a new one, but you can have also some continuous aseismic creep. You can have also some post-seismic displacement and so on. And so we'll see that we'll be able to use remote sensing to try to decomposite, to separate these different phases and to estimate to quantify their activities. So for that, we will see two main approaches. The one which is if you have an earthquake before and after comparison to study the co-seismic. And we'll see some example of time series analyzing when you have more dates. And this will allow us to study post-seismic or interseismic or transient aseismic slip. Okay. So when we do before and after comparison, could be done with several kinds of data. It could be using optical imageries. So you will see that you can use an image correlation method to infer the displacement. And we can also do similar methods with radar image using the intensity of the radar image. And also we can do that if you have some DM acquired at different dates. You can do the difference of the DM, or you can also do some correlation of the DM in 2D or 3D to also get horizontal deformation. And we will see a last method, which is the radar interferometry, which in this case will use the phase information from radar images to get measurement of the ground deformation. Okay, so let's start by the optical image correlation. So the idea is to have an image before an earthquake and an image after an earthquake. And the analysis is based on the comparison of small windows of these two images. So we will isolate small windows, zoom on that, and what we want is to be able to achieve sub-pixel accuracy that can be achieved if you compare this image using in the frequency domain. So I will not enter into the detail, but this is kind of standard method to do this image correlation and to compare these two images to see what is the best offset that make this image the most similar according to the subpixel offset you apply between these two windows. So using that, you can get offset along line and column. And as these optical images are basically north-south and east-west, you will be able to have north-south map displacement map and east-west displacement map. So mainly horizontal displacement for optical imagery. So here is an example of the north-south displacement map. The color show you the offset in this case between the line that has been converted into meters, and you can see that in these two images now you see clearly the fault that ruptured during the Hector mine earthquake in California, and to be able to quantify the co-seismic displacement along this fault for this earthquake. And the interest of having high resolution images is to be able to get very near field information. And then if you do that, you can do some cross-section along this line and to estimate at each along strike the offset due to the earthquake. And here is a comparison, for instance, between the offset estimated by analysis of images and the field measurement. And you can see that often the offset measurement from images is above this, because in the field, sometimes you are missing some distributed deformation that are not easy to spot, and that you tend to underestimate the real offset. So this is very important to combine imagery with the field work, because you have complementary information. Okay, so now we can do similar approach with optical, with radar imagery. This is the same principle, using just the intensity of the image, not the phase in this case. And here is an example of application with here for the Kashmir earthquake in 2005. So this is about 100 kilometers here. And in this case, the complementarity of radar imagery with optical imagery is you are not measuring this time only the horizontal displacement, but you will be also sensitive to the vertical displacement. Why? Because if you remember, the radar imageries are not looking at the vertical, but slightly on the side. So your pixel in column are sorted along this line of sight direction. So it means when you measure an offset along what is called the range direction, you are measuring a change in distance along the radar line of sight. So in this case, you will be able to estimate some displacement along the radar line of sight. And also if you are measuring on this direction in the north-south direction. So from that, if you combine all this information from ascending and descending orbits, so this one and this one, you will be able to retrieve some 3D information like this one. So this is the estimation of the vertical and the horizontal displacement for this earthquake. Unfortunately, the resolution we can achieve, it's difficult to go nowadays below the metric level. So it's less precise than the optical imagery, but still it can give uplift information. We can do also similar things with DM. So I just show you as an example. It's on the landslide, but the idea is the same. This is a LiDAR DM on the landslide area in French Alps. If we have two DM estimation from LiDAR acquisition, 2006 and 2009. So this is 2006. This is a zoom, and 2009, and you can see that if I move from one day to another, you can see some displacement on this part from one day to another. And so if you do the correlation between these images and you compare also the difference in DM, you will be able to retrieve the 3D displacement. So here the color corresponds to the vertical displacement and the arrows to the horizontal one. Okay, so now let's move to the last method, which is a bit more complex to explain, but I will try to be brief. So if you remember, I told you that in radar images, we are recording not only the intensity of the signal, which is goes back to the radar, but also the phase information which contain two information, an information about the relative position of the target on the ground, which is called the intrasync phase, and an information about the travel time from the satellite to the ground. So if we take one pixel, single pixel, so as we have these two combinations and we don't know at all this one, and this one could be very variable from one pixel to another. If you look only at one image of the phase, it looks like noise. So you cannot do anything if you have only one radar image with the phase. It's all not, you cannot exploit it. But the idea of the interferometry is that if now we have a second acquisition by the satellites, if you consider the same pixel here, if there is no change in this pixel, you will have again the phase you are measuring for this pixel is the sum of the travel time from the satellite to the ground plus the intrasync phase. And the idea is that if you do the difference between the two, if there is no change in the ground, these two terms will cancel out, and you will just be left with the difference in travel time between the first pass and the second pass. So if your satellite exactly pass at the same place, you will be able to measure the change of the displacement of the ground towards the satellite. So it's called doing interferometry. So you have a first image with a lot of pixels. So you do the difference between the two, and these two terms will goes out, and what is left is only the variation of distance from the ground to the satellite. So this variation of distance could be due to the fact that your satellite is not exactly passing at the same place, so it will create this kind of things. But you can also measure, this can be corrected if you know the orbits. And then if you are able to correct that, you are able to get a measurement of the displacement of the ground between one pass to another. The thing is that we are not measuring exactly the change in distance. What we are measuring is the change in distance modulo 2 pi. 2 pi corresponds to the wavelength of your satellite. So if you have a wavelength of 5.6 centimeter, you will be able to measure this displacement modulo to this wavelength. So what you will get is kind of fringes. So each time you have reach a displacement of the half of the wavelength, you will go again to a phase from 0 to 2 pi and so on. So you have not a direct measurement, but if you are able to count these fringes of colors, you will be able to retrieve the change, the range change here from one pass to another. And here is an example of two interferograms here before counting these fringes. So you get this information that show you that there is a change in displacement toward or away from the satellite. And if you count this number of fringes, it's called, you can do that automatically, which is called unwrapping. You can get this kind of images and retrieve this information. And if you have ascending and descending orbits, so different line of sight, you can also get information about the 3D deformation. Okay, so regarding this method, just to show you their complementarities on an example, here we are in an example in Taiwan. It's a reverse fault. It's an earthquake 7.6 that occurred in 1997 on a reverse fault. This is result from GPS that show you the horizontal displacement. This is result from the north-south component from optical imagery in meter here. This is from SAR image correlation. And this is the result from INSAR. So you see that INSAR, the interest of INSAR is far more precise than what we could get. We can reach centimetric accuracy, and in this case, only metric accuracy. So the big interest we have in INSAR is this very important increase in accuracy. But unfortunately, if you have too much displacement, you will lose information. So in this case, we cannot get information here because there is too much displacement. So there is a drawback in this method. So that's why it's useful to use all this method together. Okay, so now let's move to the time series analysis. So basically, I will not enter into the detail, but it's the same approach. It could be by correlation on INSAR, but instead of having just one image after and one image before, you will use a series of acquisition. Here is an example of an INSAR time series. This is available from this website. You can go there. On each of the points, there's millions of points here. And if you click on one point, you will get this kind of information, which correspond to, for each dot, one acquisition of one image. And here you have hundreds of acquisitions since 2016, and you can retrieve the displacement either along the line of sight, or if you have several line of sight in vertical or east-west displacement. And you could do similar things with the time series of optical imagery and so on. So example of application for active fault. So this is an example of the Mani earthquake in the Tibet, so along this fault. So you have several images that can be used. And here is an example of INSAR monitoring of post-seismic deformation over 4 years. So for this 3 rectangle here, you have the evolution in time of the post-seismic deformation here expressed in centimeter along the line of sight of the satellite. And you can then estimate how it evolves with time and to have information about the physical process behind this. Another thing you can do is to measure the interseismic deformation, which is the deformation of the ground, the elastic deformation of the ground that is accumulated before an earthquake, and that deform at large wavelengths the ground. So it's an example of the North Anatolian fault, in this eastern part of the North Anatolian fault, with here a result from the INSAR analysis. And if you do a profile in this direction, you can see a typical arctangent shape here that show you the accumulation of stress along across the fault, and you can from this estimate some slip right. Another example of application at larger scale here, it's most recent at a continental scale with the most recent data, we can do that. Here it's horizontal velocity field estimated, so it's in millimeter per year. You can estimate the velocity, and this is the vertical one. So you can see here, for instance, that it's easier to spot the strike slip fault in Tibet using the horizontal velocity field. For the vertical field, there's a lot of other surface processes that contaminate the signal, especially the permafrost issue, hydrological things that make the interpretation more complicated. Last example for interseismic deformation, it's a creeping fault. So faults that are creeping aseismically without generating earthquake. Here we are in the eastern part of Taiwan along the longitudinal valley fault. And here is an example of the velocity map you can get, and you see there is a sharp, here there is no earthquake, but you can see a sharp change in velocity across this fault, indicating that the fault reached the surface and is creeping, and you can measure along strike. So this is the offset, creep offset due to the offset for different part of the fault. And you can see some segmentation of the fault. So it goes up to here several centimeters per year of creep. Okay, and just to show you the interest of doing that rather than just relying on GNSS. So in color, you have GPS points. If you just interpolate this GPS point, you get this kind of image, and you can see the gain if in spatial resolution using the radar imagery with INSAR. Okay, so now let's finish with some examples, some challenging of using this. So we have seen all these methods, so which we call the space geodetic measurement. So there is some challenge when we want to use them in seismic hazard assessment. You have to remind that first we do this kind of measurement, and usually the methodology is to then try from this measurement eventually that could be combined with GNSS or some seismological information, is to retrieve the slip deformation at depth. So this is depth and the fault, and the color here shows you the slip at depth. And here is a representation of what you have seen before, the surface, the deformation at the surface. For instance, here in the case of a co-seismic offset. Okay, to do that, we rely on some modeling, which usually are assuming some elastic deformation for co-seismic displacement. And then from that, you can do some interpretation, or just starting from the data, try to interpret the geometry of the fault, and also to estimate the stress change that can be due to that are all this kind of parameters that can be used. Very important information for seismic hazard assessment. So fault mapping, segmentation, is the folding, the fault geometry, seismogenic depth. So it would be given by this thickness of the slip distribution here, by the thickness, the depth of the slip distribution, but also the slip rate. Or if you have some information about interseismic and post-seismic, you can estimate some information about the aseismic slip versus co-seismic slip. All of these are very critical ingredients for seismic hazard assessment. However, there's difficulties in this workflow. There are several difficulties that arise when you do that you have to be aware of. And I will just show you some example of this to finish. So first of all, there is a problem of data coverage and the fact that we are measuring surface measurement and we lose resolution with depth. So this is an example for the Tohoku earthquake in Japan, magnitude 9, with some measurement from GNSS. It could be also combined with some INSAR measurement. And the main slip occur offshore, and we are only offshore, and we are mainly onshore displacement. And if you do some kind of synthetic resolution test, so if we have the same network of observation and say we know the slip distribution, which is looking like this one, if we do the kind of inversion I told you, we will maybe retrieve something like that. So you more or less retrieve on land the right slip distribution, but as we don't have information offshore, we will have maybe a very distorted version of the real strip distribution. Another limitation is that as we do this kind of inversion, usually there is non-uniqueness of the solution. This is another example from here we are on it's Pakistan, along a fault here that measures several hundreds of kilometers that rupture during a large earthquake, Balochistan earthquake. So the background shows you the co-seismic displacement estimated from remote sensing imagery. When you do inversion of this data, you can have typically, you have to do some assumption about the geometry of the fault because you don't know it. And also, for instance, for these two cases with different geometry, you will get two slip distributions that equally well explain the data, and you are not able to, without other, if you don't have a aftershock distribution or microseismicity, to really say which one is the right one. Another thing which is very important for seismic hazard assessment is on seismic hazard assessment, you need to have a kind of scenario of how, what are the segment of the fault that will rupture them, and if they will rupture in cascade. And what we can see, one of the interests of using this kind of imagery here is on the example of the Kaikua earthquake in New Zealand, is that you see how complex could be a rupture, and with not several segments that are separated by some distance that can rupture in cascade in this earthquake, and show you the very big complexity, and that in some area you may have some distributed deformation, sometimes it's more localized. So all of this is very important when you compare to field measurements, to have this in mind, because if you do a trenching in this area, for instance, you will, on this point, you will estimate maybe a slip displacement, but you may maybe miss some important deformation that occurs around. So again, it's very important to combine this. This corresponds to the thing I already showed you, but this kind of result where you can compare the field measurements and the image correlation distribution of lateral offset along a fault. And again, if you do a trench in this area, you will certainly miss a big part of the displacement. Okay, last, yeah, 1 or 2 minutes left, so I will finish by that. Another limitation is when you study post-seismic deformation, is that when using imagery, you may have typical revisit time, remote sensing imagery of several days or sometimes weeks in between the image before the earthquake and the images acquired after the earthquake. So you may mix some co-seismic and post-seismic deformation. And it may have a significant impact if you have a large early post-seismic deformation. So here is an example of how it looks like, the post-seismic evolution. And you can see that here it's for 12 hours after an earthquake or 36 hours. So if you have only acquisition 1 day or 2 days or 3 days after, you may miss a big part of this. And if you assume that your first image and the image before and the first image acquired after correspond to the co-seismic, you will actually incorporate part of the early post-seismic into your co-seismic. So you have to be careful to that. And for getting the post-seismic, another issue is that you may have very long-term duration issue for very large earthquakes. So this is example of the magnitude 9.2 Alaska earthquake in 1964, and this is example from the Chile earthquake in 1960, magnitude 9.5. And if we do measurement now, 40 years after this earthquake, we still see some measurement. So you have to be careful not to integrate this post-seismic measurement in your interpretation. Because if you assume it's only interseismic deformation, you will completely miss the physical process, or you may misunderstood the reality of the physical process and make a wrong interpretation. So, okay, so, oh, yeah, just in time. So I will finish by just to say that you have seen here, I tried to show you some example of how remote sensing can be used in different ways to study active fault. But remind that usually these methods come in complement to other approaches, fieldwork, exploration geophysics, paleoseismology, GNSS seismology. So you don't have to see isolated from the other. In the last 10 years, there's big improvement in terms of access to the data and the capability to provide spatially dense measurements. So we have seen several examples of co-seismic displacement measurement, or also interseismic at continental scale measurement. So that's something you will see more and more. So I think it's good to have some basic knowledge about that. And remind you that when we go from the surface measurement to the to depth, to understand what's happened at depth, the slip, because it's what we need, the knowledge of the slip displacement at the edge and their timing. We still rely on some assumption about the geometry, which are not necessarily well known, and some limitation of the inversion process that can have significant impact of your incidences. Okay, so this is, you have to also to keep this in mind. And of course, it's also interesting to compare this observation at short term with the longer term observation we have seen, and to see if they show some change in time. And for this, we need an integrating and consistent seismotectonic framework. And here we need to go through numerical modeling and geological and seismological data to well understand that. So again, the pluridisciplinary approach is a key thing for active fault analysis. Okay, I'm done in time approximately, I hope.
Yeah, thanks a lot, Erwan. That was very good. A lot of results, and you covered a lot actually. Thanks a lot.
So it's time for question. I have one just to start the discussion. I was surprised with the checkboard analysis by Ozawa for Japan. It was actually not that bad along the trench. I thought, that it would be actually much worse than this. So I thought that people were not able, just based on online GPS, to evaluate the coupling near the trench, but this test seems to show that you can actually say something meaningful.
Yeah, of course, that's the limitation of the checkerboard also. Okay, yeah, but you're right. There is information. The question is, how you estimate this? How you translate this into uncertainty into in terms of sleep, right? It's always a bit tricky, but you're right. It's not completely maybe in this part you miss competitive things, but you still have some information. You're right.
Okay. Okay. Are there any questions, students?
Don't be shy.
Yeah, don't be shy. Okay. Well, I have although I have other questions, but that's that's not the goal, I guess. Yeah, well, just another one. I mean, when you showed for Chichi that you cannot resolve with INSAR the eastern side, is that because you cannot unwrap the phases, or what's the reason for this?
Yes, there's two reasons. The main reason is it's related to the unwrapping, but it's the fact that I don't remember where. It's the fact that the gradient of displacement is too high. Yes, so you're right. So the fringes are too narrow and mixed together. So you have an aliasing problem, a sampling problem. And in this case, you are not able to count them anymore. And then basically you lose it. And in addition to that, you have also, as it is a reverse fault, most of the you have more change in the surface on the hanging wall than on the foot wall. And in this and in relation to that, the topography is also on the hanging wall on reverse fault. So here you have, okay, in this part you are in the plane basically with cities, which is better for INSAR. In this part you have topography change and the nature of the ground that will introduce noise plus high gradient of deformation. So it's already a bad case for INSAR. Plus more vegetation. So we accumulate the difficulties.
Okay. Yeah, because I mean the displacement that you show are very different from one image to the other. I mean, in terms of amplitude. I mean, talking about meters on one side, centimeters on the suite. Okay,
Yeah, exactly. Yeah. There's 10 of centimeter on the because it's quite typical when first fault you have a big dissymmetry between well, you can see in GPS actually also. You have a big dissymmetry between the hanging wall and the foot wall in terms of deformation.
Are there any questions?
Does among all the students here who are using this kind of techniques in their PhD or are planning to use them? Some of you are using this kind of images.
Actually, in my case, I will use the hyperspectral imagery. Yeah, that's my target actually.
Yeah,
that's
you are working on
on
trenches, right?
Exactly.
Yeah. So that's why I didn't go too much into hyperspectral imagery from remote sensing, because our experience is it's more the spatial resolution which is more critical for this kind of analysis. I show that the spectral signature is less critical, I would say. But that's true for you. It's fundamental to have this spectral analysis.
Exactly. But thank you very much for the information.
I guess Mikey also will, I mean, do some, I don't know, geodesy with you, Erwan? Is that right?
Yes.
Yeah.
Yeah, I will use InSAR.
Yeah. And actually, I see Magali is around, so we will have also discussion with Magali Resna. So she's not a young PhD, but I saw she's around, so we discuss with her about the interpretation of things. But yeah.
Yeah.
Hello.
I just have another question. I want to know if there is any methods for urban area that there are a lot of human-made changes in that places. If there, I want to know if is there any ways, if any methods, any filter that you can use this method in urban area or not?
So you are looking at change detection in urban.
Yeah.
Okay, change detection that could be due, for instance, to building construction or destruction, or
no. How we can separate the human-made changes from the active faulting changes in urban area.
Okay, so you have a specific mechanism in mind. So I was thinking about, for instance, I know that pumping water, for instance, will create some deformation that could be mixed with some other kind of deformation. But maybe you have other kind of things in mind in terms of what kind of man-made activity would perturbate the tectonic signal.
Now you mentioned that we have active faulting in the urban area.
Yes.
How we can find the deformation in that places
Okay.
with this method?
I would say that urban area are quite good for the method I mentioned, especially for radar interferometry, for instance, works better in urban area than in natural environment, because you have better reflector, and they are more stable actually than vegetation. Vegetation is changing sometimes too much, and the building are more stable things, so we have better results in urban area for InSAR. It's also the case for optical imagery or image correlation. The urban area is not necessarily a problem, because we are looking at actually a feature that from which the properties doesn't change, but that we can track their displacement. So, and the urban feature are quite have some right angle and things like that, so are good to do some correlation. So for LiDAR, InSAR, or image correlation, it's not a problem to work in urban environment.
So the coherence is better with.
Yeah, definitely, yeah.
Okay.
Yeah,
And there's no problem with like traffic or things like this.
Okay, so yeah, if you have a very high resolution, of course you may have some problem in the roads and so on, but if you capture, I mean, most of the things are stable in the city. It's what we see actually. But yeah, that's why that if you start to work at the you need to filter maybe some area where you may have change in evolution.
Thank you.
Okay. Just a last question from me. You mentioned at the very beginning that a constellation with hundreds of small satellites. So it's actually deployed already, yeah?
Yes, Planet Lab. I don't know exactly how much they have now, but yes, they have already quite sent a lot of them. I haven't the number, but yeah, the order of magnitude is hundreds.
Okay, so I mean, are people like in Earth science using this constellation specifically?
Yes, it starts to be used. The problem is that they are their spatial resolution is not exceptional, and the stability of the satellite is also less constrained than on a larger satellite. So you may have some correction to do before, but James Hollingsworth, for instance, in our lab is using this kind of image. So there is some challenge with them, but as you have a good revisit time, it starts to be useful. There is also starting this kind of constellation with radar images, not usable for InSAR, but for image correlation that could be used.
Oh.
Yeah.
Impressive. Okay, good. Last question by anybody? Well, okay. Apparently not. So thanks a lot, Erwan, again.
Thanks.
Thanks everybody for
My
attending.
pleasure.
So we'll be back in 2 weeks' time. So in the meantime, make a lot of progress on your PhDs, and see you in a fortnight then. Okay, bye-bye, everybody.
Bye.
Thank you very much. Bye bye.